Our task in this lecture is to dive a little bit deeper into the SN curve so that we can do lifetime predictions. So the first thing that we always do when we're looking at fatigue and trying to estimate the lifetime of a component is we have to figure out what the endurance limit is. The other thing is, can we predict in the high cycle fatigue regime, can we apply an equation to it? And you know what that is. That's Basquin's law, that the fully reversed stress amplitude is related through some constant to the number of cycles to failure to an exponent b. So you're always trying to find this sigma AR, which is a fatigue strength that is associated with a specific number of cycles to failure. And in order for us to do that, we need to know the constants A and B. And we're going to have to come up with means for estimating what those things are. So if we look a little bit more closely at this curve, then you will see that this point right here at 10 to the third cycles is going to be at a fatigue strength that really is a fraction of the ultimate strength. So we need to know what that fraction is. So we're saying that this is some fraction of the ultimate tensile strength. And there are ways for us to estimate what those fractions happen to be. You will recall, I hope, that in the Coffin-Manson law, the high cycle fatigue regime is dominated by the elastic strain. So we're going to use our understanding in the high cycle fatigue regime to tie ourselves down at these two endpoints. And we know that this endpoint on the left is at 10 to the third cycles. This endpoint on the right is at 10 to the sixth. So if we look at the Basquin's law equation, we know that at 10 to the 6 cycles, the fully reversed stress amplitude is simply the endurance limit. And at n equal 10 to the third cycles, the fully reversed stress amplitude is going to be some fraction of the ultimate tensile strength. And that's an important thing here. So what have we found out? Well, people have done a large number of experiments, and they have determined two key findings. The first is that the endurance strength is half of the ultimate tensile strength so long as that ultimate tensile strength in English units is less than or equal to 200 kpsi, which corresponds to 1400 MPa in metric units. And then you decide that if the ultimate strength is larger than 200, or in metric larger than 1400, then we simply limit the endurance strength to 100 kpsi or 700 MPa. That is, so this curve right here is the experimental data that supported equations 6-8 up above. That is, they found a relationship between the endurance limit and the ultimate tensile strength of a material. This relationship, you'll note, is called SE prime. So SE prime is something that we're going to use, and it's associated with 10 to the 6 cycles to failure. So let's take a look for a moment at Basquin's law, where sigma AR is equal to some constant times NF to the B. But then we're going to transition and go back to the second part of Coffin-Manson. And you may recall that the Coffin-Manson law relates the total strain amplitude to the elastic strain amplitude and the plastic strain amplitude. And we're going to focus on this part because the elastic strain amplitude, we said, was related to the sigma F prime over the elastic modulus times the number of reversals to the power B. So there's the rub that we're trying to sort out. And what we do is we multiply that elastic modulus times this elastic strain amplitude. It's going to be equal to sigma F prime times 2n to the B. It turns out that sigma F prime in the English units is just the ultimate tensile plus 50 kpsi, and sigma F prime in metric units is just ultimate tensile plus 345 MPa. So that gives us sigma F prime. So now we have an equation where we know that F times SUT is going to be equal to sigma F prime. That number of cycles to failure is 10 to the third. So we have an equation right here. We have one equation, and we still don't know B, and we don't know F. So now we go to the number of cycles to failure being 10 to the sixth. So at 10 to the 6th, the sigma AR, which is called the fatigue strength, is simply going to be equal to the endurance limit. And so the endurance limit, and it's called a prime because we're going to estimate it, is equal to sigma F prime times 2 times 10 to the 6th cycles to failure to the power B. We use the equations above to find the sigma F prime, and we use our estimate of the endurance limit. So if ultimate tensile strength is less than or equal to 200 kpsi, then SC prime is 1/2 the ultimate tensile strength. Likewise, if it's less than or equal to 1400 MPa, then the endurance limit is equal to 1/2 the ultimate tensile strength. So whether English or metric units, it's easy for us to find the endurance limit, and that then gives us a second equation. We use the SAE method to estimate sigma F prime, and then we have two equations for the two unknowns, B and F. This allows us to solve, so we solve for B and F from these equations. You will find that the fraction F that relates the fatigue strength, FSUT, at 10 to the 3rd cycles can be plotted, and here it is plotted as a function of the ultimate tensile strength. Unfortunately, the book only gives this to us in English units, but if you have the ultimate tensile strength, you can find the fraction F that is related to the ultimate tensile strength, which then allows you to find the fatigue strength at 10 to the 3rd cycles. So it's not a particularly difficult thing to do. So we know that 10 to the 3rd cycles, we have a fatigue strength of FSU and at 10 to the 6th cycles, we have a fatigue strength that's equal to SE prime, and we find the SE prime and this F using the curve that we just discussed, and SE prime using our relationship between endurance strength and ultimate tensile strength. So if you have that F and you have that SE prime, it turns out that if you simply write Basquin's law again in its simpler form, this is the same thing as sigma AR being equal to capital A NF to the B. I've just replaced capital A by little a. B is the same. You look up the F, you know the ultimate tensile strength, you calculate the endurance limit. This gives you A. And for B, you know F, you know SE. You have the two fitting parameters you need to do a high cycle fatigue cycle count prediction. Now, the best thing we can do is an example. This is an example from the book where they ask us if we're using a 1050 hot rolled steel to estimate the rotating beam endurance limit at 10 to the 6 cycles. So we are trying to find SE prime. Well, we got to go to table A20 in Shigley, and it says for the 1050 hot roll that the ultimate tensile strength is 90 kpsi. Since ultimate tensile strength is less than 200 kpsi, then the endurance limit is going to be 1/2 the ultimate tensile strength. So the endurance limit is going to be 1/2 90 kpsi. It tells us the endurance limit is simply 45 kpsi. That corresponds to a lifetime of 10 to the 6 cycles or greater. And I mentioned the 10 to the 6 because that pins down the end of the high cycle fatigue regime. So the next question here, we've answered the first question. We find the endurance limit. The next question says, what's the endurance strength of a polished rotating beam specimen corresponding to 10 to the 4th cycles to failure? So we want, not the endurance strength, we really want the fatigue strength. We want SF prime corresponding to a lifetime of 10 to the 4th cycles. So that puts us squarely in the high cycle fatigue regime. That NF is greater than 10 to the 3rd and less than 10 to the 6th, so it is the high cycle fatigue regime. And in that regime, we know that we can use the fully reversed stress amplitude equal to A times the number of cycles to failure to power B. So now we got to find A and B. And the way we're going to find A and B is we're going to go back to our equations. So now what we're going to do is we're going to go to Shigley and we're going to use equations 613 through 615. Well, 613 is just Basquin's law once again. And now we have to find the fitting parameters. We're going to use what we've just discussed to find those fitting parameters. And that is the fitting parameter A is equal to FSUT ut squared over SE prime. We know that SE prime is equal to 45 kpsi. We know that the ultimate strength is equal to 90 kpsi. And we know F, well, we're going to go to this chart right here, and we're going to look at 90 as the ultimate. Come up here, we're about F equal 0.86. So we take this 0.86, multiply it by 90 kpsi. We square all that and divide by 45 kpsi. And we find that A is equal to 133 kpsi. So there's my factor A. Now I have to find my factor B. And you'll notice from equation 615 that B is equal to minus 1/3 times the log of F SUT divided by SE. F is 0.86, so we get minus 1/3 times the log of 0.86 times the ultimate, which is 90 kpsi, divided by 45 kpsi. When we do that calculation, we find that B is equal to minus 0.0785. So now we have what we need to predict the fatigue strength associated with 10 to the 4 cycles. We say that the fatigue strength is going to be equal to A, 133 kpsi, times the number of cycles. That's 1 times 10 to the 4th cycles, raised to the power minus 0.0785. And if we do that, we find the fatigue strength is given by 64 kpsi. The last part of the problem, part C, shown here, wants to know the expected lifetime of a polished rotating beam specimen under completely reversed stress of 55 kpsi. Completely reversed, so we can use the stress amplitude of 55. So we know that SF prime is equal to A and F to the B, and we know that A is equal to 133 kpsi. We know that B is equal to minus 0.0785. And so we simply put the 55 kpsi on the left side, and that's equal to the 133 kpsi, the number of cycles to failure, to the power minus 0.0785. Solve for NF, which says that I have 55 divided by 133, all to the negative 1 over 0.0785. And if we do that calculation, we find that the number of cycles to failure are 7.7 times 10 to the 4th cycles.